In this video, I'm going to walk you through a model that I've created that simulates a personal investment program, um, specifically for someone who is in retirement or planning to retire very soon, that tracks the growth of their retirement investments and takes into consideration other sources of income such as Social Security or retirement pensions, um, as well as their income need, um, and tracks the withdrawals from the investment such that the requirement is that the balance of their retirement investment never falls below zero. So let me first talk about the actual model itself. This is composed in using SysML um, opaque actions entirely. So there are no behaviors other than opaque actions in this model. Um, it's done as a loop, which means that we've defined a variable that I'll talk about. It's called count. And so the count is set to increment by 1, and we have a variable called year, or a value property called year, that I'm going to show you in just a minute, that we plug in. So the idea is that this activity diagram will execute one loop for every year. And that number of loops is then defined as the number of years. And with probability 1, then the loop will exit. Probability 0, which is loop number 2, then it will go back to this merge node here and then continue. The first, or rather I should say the next opaque action is we've put in a provision. So if the count is equal to 2, that is at year number 2 from when we start this simulation, we have provided the possibility of adding a lump sum to our retirement balances. And you could define the default value of that lump sum however you want. If you don't want a lump sum, you can just leave that as 0. Or you can also change the year at which you want to put in that lump sum. It could be at year 3 or 4. The next opaque action is, for example, if the retiree owns a home and the mortgage is going to be paid off at a certain point in time, then the annual income need will be reduced by the annual amount of the mortgage, including the taxes and insurance and interest. And so in this case, the retiree's mortgage will be paid off and we're assuming the retiree is 65 at this point. Their mortgage will be paid off at age 79. So that's 14 years from now, so that reduces the annual income need. So then we calculate the retirement balance as the default value beginning at year 0 plus the retirement balance times a return on investment, which is the assumed rate of return on the invested funds. And then you subtract from that any withdrawals that you take out of those retirement balances. And I'm assuming that this is an IRA, an individual retirement account, that these funds are in. So then you can see that we now have a fork node where these 4 opaque actions take place in parallel. The annual income need is decreased by an assumed inflation rate. So we increase the annual income need each year by the rate of inflation. Social Security, we're assuming that this individual retiree is married and that the spouse is also receiving Social Security benefits, if any. So the Social Security for spouse number 1 is going to be equal to whatever the monthly benefit is, or in this case the yearly benefit, adjusted for a cost of living, and so a cost of living allowance, or COLA. So in this case, in this model, we've assumed an annual inflation of 3% and a cost of living annual of 2.5%. So that is also replicated for spouse number 2's Social Security income. And then this opaque action here would be if there's an annual pension, that's the annual amount, and that we're assuming the annual pension is increased every year by the cost of living adjustment. So these three things get incremented by the inflation rate or the cost of living rate. And then finally, the last opaque action calculates now the new IRA withdrawal amount, which is going to be the annual income need minus both spouses' Social Security, minus the pension. And I also have PT work, which would be any, say, part-time work that a spouse then would do. And so if we have another year to go through, then it's going to take the probability of loop 2, which is probability 0, and then it's going to execute. So just doing a really quick simulation, we can start this and show you that it's going to just run right through these opaque actions and then circle. So I'm going to stop the simulation there and go back to the navigation page and talk about the value properties. This is, let me magnify this a little bit so you can see it better. This is a table where the user then can adjust the default value. So the annual income need, the default value is the need at year 1. So we're saying that that annual need is 135,000 and the type is in dollars. This is the count variable. Its default value is 0. The cost of living adjustment assumption for Social Security and pension is, as I said, 2.5%. The value property for inflation is 3%. The initial withdrawal from the IRA for that year, first year, is listed as $45,000. These are the two loops. The path to activity final is going to be with probability 0, and the path to increment the count to the next year is going to be with probability 1. Here is the value property where you would add a lump sum. So, for example, the activity diagram has the lump sum being added at year 2 when count is equal to 2, and that would be $52,000. And you'll see how that we can adjust that and change the goal. The annual pension, in this case, $36,000 roughly. No money from part-time work. The starting balance for the IRA we're saying is about $785,000. Return on investment is, we're going to say, 6.7%, and these are the Social Security amounts annually for spouse number 1 and spouse number 2. And the retiree is currently 65. So what I'm going to do is change this default value to 10 years. So we'll see what the retirement balance is going to be in 10 years given these constraints. We have the model results in this instance table. So when we run the simulation configuration, which is listed here, so we don't have a user interface for it, we just have the execution target as the investment model itself, and the result location is going to go into the model results instance table. So now we have up here the simulation configuration, so I'll bring that over so you can see it. So let's go ahead and run it, and we'll just speed it up, and we'll go over to the model results, and here's the instance, and we'll drag it over here. So you can see that after 10 years, given these values and the lump sum at year 2, we have a retirement balance of $875,000. So even though money has been taken out, the retirement balance is increased, and that is something that you would expect. We've also, at year 10, the IRA withdrawal is now $66,000. The pension is up to $46,000. The Social Security for spouse 1 is up to $26,000, and for spouse 2 is 42,000. And the annual income need, you'll note, too, has increased because we're accounting for inflation. So what started out as 135,000 is now $181,500. So let's change one thing. Let's go back to our value properties, and let's change the year to 20. And we'll do another simulation and go back to model results, bring that instance over. Now you can see that the retirement balance is starting to decrease, and again you would expect to see an increase in the first few years and then eventually a decrease, because as you can see, the IRA withdrawal is increasing each year, and if the percentage of the IRA withdrawal is greater than the rate of return, you're going to see the retirement balance decrease. And you can see here that this is like 9% or something of that retirement balance, so that's greater than the 6.7%, and so then you would expect to see a decrease. Let's go ahead and do the full. We'll take it out to, say, age 95. So that would be 30 years for a person age 65. Sorry. So 30 years. Let's go ahead and simulate that and go back to our instance table, and we'll bring that instance in. And you can see that even at the 30-year point at age 95, there's still $289,000 left in the retirement balance. But you can see the IRA withdrawal now is 108,000, so it's not going to last very much longer, because that is getting close to half of what's in the retirement balance. But you can see the annual income need is almost $300,000 now, because we're 30 years in the future accounting for inflation at 3%. So this is a model that is very useful in and the actual block that holds all these value properties and that provides the content, or rather the context for this activity diagram is that block right here. So that's the structure of the model. But now what's interesting is you can add variability, because what happens if we have some uncertainty surrounding the rate of return? Maybe our return is going to be more than 6.7%, maybe it's going to be a little bit less. So what we've done in this version of the same model is we have now added a random component. We have then created or taken our value property. Let me go back to the value properties, and I'll talk about the ROI, because you can see it's a little bit different there. So let me open up the specification, and you can see that the applied stereotype for this is not just a value property, but we have the ability to turn it into a random variable, a normally distributed random variable that would have a mean and a standard deviation. So in this case, we have selected the mean at 7% and the standard deviation of 0.2%. So that's what we're going to do in this setup. Everything else stays the same. The annual income need at year 1, the cost of living increase, the annual rate of inflation, the initial withdrawal from the IRA. What we have done, and I'll show you how this works, I have deliberately used this because we're going to be generating a Monte Carlo simulation. I should have gone back and explained this. We have 2 histograms, one that's going to track the retirement balance, which is what we're interested in, and also the return on investment. So we've set dynamic to true, and we've set silent to true, and the execution target is still the block that holds the value properties, but now we've added the the UI for histogram. So again, as I said, we're going to simulate this all the way out to age 100 because actuarially, probably very few of us are going to be alive at that point. So that's kind of a reasonable target. The only other thing I want to include is we now have a requirement. So our requirement is that the retirement balance throughout all these years be greater than zero. And since I've turned on the global glossary, I've been able to extract a constraint block that basically says X, our variable of interest, it must be greater than zero. And so I've got that tied to the retirement balance with a satisfy relationship. So what that's going to allow us to do is to determine whether or not we have met the requirement. And so you'll see that. So let's run the simulation, and remember that we're going to run 30. It's one loop of this simulation here is going to be equal to 1 year. So keep in mind that when you do a Monte Carlo simulation, one run is going to be 35 loops if the number of years we're looking at is 35 years. So it's not going to run really fast. So if you put in 1,000 runs, which is what we did, it's going to take a long time. So I'm only going to let it run for about 100 runs so we can see what the results are. So let's go ahead and run the simulation. So you can see we have the return on investment, and we have the retirement balance. Let me bring those out. So we now are running up to let's see, 20, 21 runs, and you can see over here that what it says out of spec. That value is the number of runs in which the retirement balance did not meet the requirement of being greater than zero. And the reason that I chose that value of the lump sum, given the return on investment of 7%, because you can see that the ROI is distributed around a mean of 0.07 and a standard deviation of 0.002. So you can see that sometimes we get a rate of return as low as 6.5% or as high as 7.5%. But it's going to be variable between that, randomly on each of the runs. So now you can see we're up to run number 80, and our out of spec is about 0.35. Which is good, because that means that most of the time, like 96, 97%, 98% of the time, when we do this run, we're going to achieve our objective of, by age 100, ensuring that we have no more than zero retirement balance. So here's, and because of the nature of statistical distributions, the central limit theorem tells us that because we have a normally distributed random variable, the actual retirement balance is also going to be normally distributed. So that's basically what we're seeing, is a normal distribution. And if I go to the results content page, you can see that for example, if we used an $80,000 lump sum at year 2, we would meet the goal of $0 or more 93% of the time. The out of spec is about 0.07. But what we just did with a lump sum of $90,000 at year 2, we meet the goal of $0 or more in the retirement balance at age 100 98% of the time. So again, you can see that you can use a model like this with loops to simulate annual increases or decrements of retirement balances and incomes, and you can collectively track them using these opaque actions and record them either as a Monte Carlo simulation, which would be ideally what you would want to do with multiple runs, or you can do the the individual deterministic viewpoint and then capture what the retirement balance is going to be at the end of any specific number of years. So thank you for watching, and if you have any questions, I'm sure that you can post them here on this MBSE execution channel, and we'll try to get back with you.